The Bermuda Triangle story always sounds like the ocean picked someone, but the real explanation is way less magical and way more repeatable. Fast current, sudden boundaries, deep drops right next to shallow hazards, and weather that flips the situation before you even realize you're off course. Forget paranormal, this is the science version. The first thing to understand is that the Bermuda Triangle isn't an official place. There are no agreed borders, no warning lines on navigation charts. NOAA doesn't recognize it as a special hazard zone, and neither does the US Coast Guard. What does exist is one of the busiest stretches of ocean on Earth. Major shipping lanes cross here every day. Transatlantic flight paths pass overhead constantly. Add changing weather systems, shifting winds, and strong ocean currents, and you get a region where small navigation errors can grow quickly. When incidents happen here, they don't mean something mysterious is pulling people in. They mean traffic is high, conditions change fast, and mistakes don't always get a second chance. To understand why this region earned its reputation, you have to stop looking at the legend and start looking at the water itself. Now we get to the most underestimated factor in this region. The water itself is moving. Not waves. The ocean, the Gulf Stream runs through this part of the Atlantic like a river in the sea. And NOAA notes that its surface flow can be fast. The maximum is typically about 9 kilometers per hour, roughly 5.6 miles per hour, and average speeds are closer to 4 miles per hour. That's close to 5 knots at the high end. Here's why that matters. If you cross a current like that at an angle, it pushes you sideways the entire time you're moving forward. And the dangerous part is how quiet it can look. The sea can appear normal. Your heading can feel correct. The horizon looks the same. But underneath you, the surface layer is sliding. So drift doesn't arrive like a punch. It arrives like a slow leak. You keep going. You keep believing you're on track. And then you realize the math has been working against you the whole time. That sideways push adds up over hours. And the risk isn't just being off a little. The risk is what comes after. Because once you think you're in one place, when you're actually somewhere else, every decision gets weaker. Routing gets messier. Timing gets wrong. Weather avoidance becomes guesswork. And even your confidence in what you see around you starts to lie to you. And the Gulf Stream isn't uniform like a straight canal. It has edges, boundaries, places where the texture of the surface shifts, and the drift rate changes fast. You can move from slower water into faster flow over a relatively short distance, especially along the edges. That means two vessels that look close on the surface can be in different water. One gets pushed harder, the other doesn't, and if you don't realize you crossed that boundary, your mental map stops matching the real ocean. This is why the Gulf Stream has shaped navigation for centuries. Used correctly, it can save time. Ignored, it can quietly steal it. In a high-traffic region like this, that invisible sideways force alone explains a huge piece of the so-called mystery, without needing anything supernatural. Now we add the factor that turns manageable conditions into dangerous ones: wind. When wind blows in the same direction as a current, waves stretch out and flatten. But when wind blows against a strong current, the ocean behaves very differently. Instead of long rolling waves, the water gets steeper. The spacing between waves shortens. And the surface becomes chaotic, not because the storm is stronger, but because the current is resisting the waves. This is a well-known effect in oceanography and marine navigation. When wind opposes a current, wave height and steepness increase far beyond what the wind alone would normally create. That means the ocean can go from manageable to hostile over a relatively short distance. You don't have to sail into a storm. You can cross a boundary where wind and current collide. And that's what makes this combination dangerous. The change isn't gradual. It can feel sudden. One moment the sea looks rough but workable. A short distance later, the waves are sharper, faster, and harder to predict. The bow starts slamming instead of riding. Timing gets harder. Mistakes get punished faster. This is especially risky in regions with strong currents like the Gulf Stream. If the wind shifts direction, or if you cross into a faster part of the flow, wave behavior can change before you have time to adapt. This is how vessels get overwhelmed without ever encountering extreme weather. Not by one dramatic event, but by physics stacking conditions against them. And when this happens at night, or in poor visibility, or with crews already fatigued, the margin for error collapses quickly. Nothing supernatural is happening here. It's wind and water working against each other, and the ocean always wins. This is intentionally dense and calm, so canvas stretches it naturally. Now we get to the part most people never picture when they think about Bermuda. What's under the water? Bermuda isn't sitting on a flat seafloor. It sits on top of a raised volcanic platform surrounded by much deeper ocean. That means depth changes here aren't gradual. In some places, the seafloor drops thousands of meters over relatively short horizontal distances. This matters because ocean behavior changes with depth. Waves interact differently as they move from deep water toward shallow shelves. Currents can bend, speed up, or shear along those edges. From the surface, everything can look calm and ordinary, but underneath, you're moving over steep underwater terrain, more like a submerged mountain than a gentle plain. This kind of bathymetry compresses margins. If you're pushed off course by current, you don't just drift into more of the same water. You drift toward depth changes, reefs, and shelf edges where conditions can change quickly. And that's what makes this geography dangerous in the real world. Not because it's mysterious, but because it's unforgiving. Steep seafloor, shallow platforms, strong currents, and heavy traffic all stacked together. That combination doesn't need myths to produce accidents. It just needs time. Now add the quiet danger, shallow water. On a map, Bermuda looks like a tiny dot in a huge ocean. But around it are shallow platforms and reefs. In daylight, that's beautiful. In the wrong conditions, it's a hazard. Here's the problem. Currents don't just push you in a straight line. They push you while you're trying to navigate, while visibility changes, while weather shifts. So if your position estimate is off, even a little, you can drift toward shallow water without realizing it. And shallow water changes the sea. Waves can steepen and break differently as they interact with reefs and shelves. So the same wind that feels manageable offshore can feel harsher and more chaotic near the shallows. This is why real incidents rarely have one cause. It's usually stacked: drift plus visibility, drift plus fatigue, drift plus weather timing, and then shallow hazards waiting at the end of that chain. The legend makes people look for a single mysterious force. But the real danger is boring and brutal. Small errors compounding in a place where the ocean gives you less room to recover. And that's the pattern you keep seeing here. Not magic, margins collapsing. This is the part where the legend usually takes over, because people see a pattern and want one dramatic cause. But clusters don't require anything supernatural. They require three normal things happening in the same place: traffic, physics, and human limits. Traffic means more opportunities for incidents. Physics means the environment can amplify small errors, current drift, sharp boundaries, and sea states that change faster than people expect. And human limits mean fatigue, assumptions, and small navigation mistakes happen everywhere, but they matter more when the margin is thin. So the Bermuda story isn't that the ocean is haunted. It's that this is a region where mistakes compound quietly. Drift puts you in the wrong water. Wind against current makes waves steeper. Shallow hazards wait where you don't have room to recover. And if visibility is bad or the timing is wrong, the situation can collapse faster than it feels like it should. That's the science version, not magic, margins. If you want the next breakdown, subscribe. We're staying real world only. Maps, ocean physics, and the actual mechanisms that make places like this dangerous.